Okay, I'm going to take you through the solutions to the problem sheet for CIVE1560 vector algebra for the year 24-25. Okay, sheet consists of 5 questions all on vector algebra. First question is about using the geometric method to solve some vectors. Now, what this means in the geometric method is to essentially draw the vector force diagram and solve this using the cosine rule and the sine rule. Or either of those. So essentially we're adding vectors, say A and B, to make vector C, and this is what we'll do in each of the calculations. In question 1, we'll see that there's 3 calculations. So let's start looking at question 1 here. We've got 2 forces act on a hook, as shown in this diagram, figure 1. Determine the magnitude and angle relative to this horizontal line of the resultant force. The resultant force is going to be, I'm guessing, somewhere down here. We'll call it R. That's what we're trying to do. First thing to do is to draw your diagram of forces. Okay, I'll draw this a little bit big. Let me make it a bit smaller. Okay. So we've got diagram of forces, and we've got, if we look at the cosine rule, we've got this 300 is equivalent to the A, 600 equivalent to B, R is equivalent to the capital C, and this angle here is the lowercase c. And we do, we've probably got enough there. So let's have a look at what we need to do to write out the solution. Right, let's just write what we've got. We've got F1 is equal to 300 newtons, which is equivalent to A. F2 is equal to 600 newtons, equivalent to B. We have the angle C is equal to 140 degrees. Now you need to get that, you need to decide that from doing the geometry yourself. But essentially we've got this at 30 degrees, we've got this one at 70, so we can see that that's 110, so 110 and 30 is 140. So we'll use the cosine rule. What we're trying to get is this value of R, or C. So C squared is equal to 300 squared plus 600 squared minus 2 times 300 times 600 times cos of 140. C squared comes out to be 725,776. You may not ever see this if you do it on the calculator. So C equals R is equal to 851.9 newtons. So there's our solution. The angle that we want to find, I'll just go on this in green, we want to find this angle. But in fact, first of all, we're going to calculate the angle inside the triangle and add 30 to it. So sine rule, we're going to use the sine rule form. C over sine capital C equals B over sine B. So in this case, B is the unknown. So what do we have? We have C, so 851.9 1.9 over sine 140 equals B 600 over sine call it theta, sine theta, and this goes to theta is equal to 26.9 degrees, and then the angle of R2 horizontal equals 30 plus theta, which equals 56.9 degrees. Okay, so the whole of question 1a. We're going to now look at question 1b, which is looking at a frame with a single vertical force down, 500 newtons. We've got a couple of angles here, 35, 40. We want to find the component of that force in these two structural elements, AC and AB. Okay, first thing to do is to draw your vector diagram of forces. So, and close the triangle. Now we've got 500 is vertical here, so I've transformed it over to there. We've got an angle here, 45. We can get 35 of this angle, and that gives us ability to calculate the unknown there. So we want to calculate the forces in AC and AB. So we can just use the sine rule. In this form of the sine rule, we'll use AC over sine 45 is equal to 500 over sine 35. And this comes down to AC equals, well, you can write out the whole thing, sine 45 times 500 over sine 35, and then the number we get is 858.5 newtons. For AC, sorry, AB over sine 100 is equal to the same 500 over sine 35, and this goes to AB equals 616.4 newtons. Okay, pretty straightforward. The trick is getting your diagram right and the angles correct in the first place. So, question 1c. Consider the force acting on this bracket. So we have a bracket, we have a force F acting upwards like that, which is unknown, but we have a force of 600 acting at 13 degrees here. And if the magnitude of the resultant force is to be 500, so the resultant force of the 600 plus F must be 500, directed along the positive axis, so this needs to be, the resultant needs to be acting up here, R. Determine the magnitude of the force F and its direction theta, this angle theta. So the first thing to do is sort out your angles and diagram of forces. So I've done this in this diagram here. I have F here, 600 here. I have F equivalent over here and 600 equivalent over here. And from our parallelogram, rule of forces, the angle, the resultant is here, R we'll call it, and that we're told that needs to equal 500. So the unknown in this equation, in this situation, is F and this angle here. We can use the cosine rule. Let me do the writing in black. So we have F squared is equal to, well, we'll do 500 and 600. 500 squared plus 600 squared minus 2 times 500 times 600 times cos 103, which we've got from the geometry, 103. And that turns out to be F is equal to 863.1 newtons. From the sine rule, we can write, now I've got gamma in this triangle, so we're just using this triangle. We have 600 over sine gamma is equal to 863.1 over sine 100. We can rearrange this, and this goes to gamma is equal to 42.6 degrees, but we're asked for theta, so theta here equals 90 minus 42.6 degrees equals 47.4 degrees. Okay, straightforward. All of these geometric problems are using the cosine or sine rule. The key to getting these correct is being able to draw the diagram correctly with the correct angles. So understand and practice your geometry. Let's have a look at question 2. Now, we have two ropes on a bracket. On these two ropes, I've got a force acting 300 and 500 Newton. And all the angles are defined for each of the ropes. So express each force in a Cartesian vector form. So we need to get things into a vector form, the forces into a vector form, and then calculate the resultant force. Well, that'll be easy once you've got them in vector form. We just add the two vectors, F1 and F2. Find the magnitude and the coordinate direction angles of this resultant force. So the first two things are to do are to get each force into vector format. Now, what we need to do is really understand what diagram we've got and the geometry of the situation. So let's see, we've got F1 and the magnitude. This is not a vector in this statement. It's 300 newtons. We've got alpha 1 is the angle with the x-axis, is 90 minus 25 degrees, 65 degrees. Beta 1 is the angle with the y-axis, is 25 degrees. Gamma 1 is equal to minus 35 degrees. F2 magnitude is 500 newtons. alpha 2 is equal to 120 degrees, angle with the x-axis. Beta 2 is equal to 45 degrees, angle with the y-axis, and gamma 2 is equal to 60 degrees, angle with the z-axis. Now we're going to use the direction cosines, and I'll just write down this formula. Because this is what we're going to be using quite later in the question. So cos alpha equals x over the magnitude of the vector. Cos beta equals y over the magnitude of the vector, and cos gamma equals z over the magnitude of the vector. Now, for f1, to get f1, we're going to resolve into the plane of the axes, xy axis, and then we're going to resolve into the plane that we need, the axis that we need. So f1, we've got r equals 300. We're going to use that. So x is equal to cos 65 times cos minus 35 times 300, which equals 103.9. Y is equal to cos minus 35 times 300 times cos 25, which equals 222.7, and z is equal to cos minus 35 minus 90 times 300, which equals minus 172.1. Okay, so we've got all the x, y, z's and r's for these direction cosines, so we could calculate the angles, but let's just first calculate the other vector vector components. So r, maybe I could just label these x1, 1, 1. R2 is equal to the magnitude is 500. X2 is equal to cos 120 times 500. That comes to minus 250.0. Y2 cos 45 times 500 equals 353.6. Z2 is equal to cos 60 times 500, which comes out to be 250, positive 250 this time. The resultant, FR, is equal to F1 plus F2, these vectors, and they're simply just add the components. So x1 plus x2, comma, y1 plus y2, z1 plus z2, which we can write down again, 103.9 minus 250, 227, let me correct it, 222.7 plus 353.6 and minus 172.1 plus 250, which, you know, your simple arithmetic gives you minus 146.1 for the x component, 576.3 for the y component, and 77.9 for the z component. I'm just going to add an extra page in here. The magnitude of f, fr, is equal to the square root of each of the components squared. So just the Pythagoras, 146.1 squared plus 576.3 squared plus, let's keep that in the square root, 77.9 squared. And that all calculates to 599.6 newtons. We could probably just say this is 600, but we'll leave it for now. Now, we have cos alpha equals x over r. So alpha is equal to cos to minus 1 minus 146.1 over 599.6, which comes out to be 104.1 degrees. We have cos beta equals y over r, so beta equals cos to the minus 1 of 576.3 over 599.6, which comes out to be 116.0 degrees. And we have cos gamma equals z over r, so gamma cos to the minus 1 of 77.9 over 599.6, which comes out to be 82.5 degrees. Okay, so we worked out the angle and the magnitude and the force vectors of each of the two forces. Force vectors of the two forces, the resultant and the angle of the resultant. Okay. Let's go and have a look at question 3. So question 3 is looking at this frame. There's a frame that's fixed at the bottom. It's got a column up here, an arm up there, and then it moves to the right. So there's an angle between the point A at the end and the column, which is fixed to the ground. Let me just go about that line. We have one force acting, F, 65 along the line from A to D, so it's at an angle. You need to just look at this carefully, this diagram. The key things to look at are these coordinates drawn here, because we need the specific coordinates of each of the points in the frame so that we can work out vectors, vector directions, etc. So the first thing I would suggest to write down is the coordinates, or the information we have. Now A is equal to minus 1.531, B is equal to 0.31, C is 0.01, it's just up the vertical, and D is further up the vertical, 0.02. Sorry. Get the Z there. 2. Remember that F is equal to 65 along a line AC. Sorry, not AC. Remember, looking at the diagram properly, along the line AO. But we've got, this is not correct either. This is along the line A to D. Remember, F is acting A to D along that line. So let's just write down the vector line AD, which is just A minus D. So, sorry, D minus A. So it's 0 minus 1.5. 0 minus 3, 2 minus 1. So AD is 1.5 minus 3, 1. That's the vector AD. I'm going to calculate AO because the question is asking for the magnitude of the force along the line AO and along the column OD. So the magnitude of AD, let's first get that because we're going to need that magnitude, is square root of 1.5 squared plus minus 3 squared plus 1 squared, and that comes out to be 3.5. Magnitude of AO is also going to be the same size, which is the square root of minus 1.5 squared. This is the same as 1.5 squared, the square plus the square root of 3 squared plus 1 squared is 3.5. We're also going to, because we've been asked to calculate force and action OD, we're also going to need the magnitude of OD, which will be just square root of 0 squared plus 0 squared plus 2 squared, which equals 2. If we want to write the force as a vector, remember what this is. This is going to be the force divided by the magnitude, so a unit vector, times by the vector. So 65 over magnitude of AD, which is 3.5, times AD, which was 1.5 minus 3, 1. We could write that out explicitly, or we could leave it as fractions. I'll just write it for you. 27.9 minus 55.7, 18.6. We need the unit vector in direction AO if we're going to calculate the magnitude, the component of the force in AO. unit vector AO is minus OA over a magnitude of AO, which is 1 over 3.5 times 1.5 minus 3 minus 1. We can write that out explicitly as well, 0.43 minus 0.86 minus 2.9. Then the force in the direction AO is equal to the force vector times dotted with the unit vector AO. And we can do that dot product and it comes out to be 54.4. Dot product or scalar product. There's an answer for OD. Unit vector OD is equal to OD over magnitude of OD, which is 1 over 2, 0, 0, 2, which equals 0, 0, 1. It's a bit more simpler arithmetic here, but you do need to do the dot product. So a F OD is equal to the magnitude of F times the unit vector OD, which you can do that scalar product or dot product, and that comes out to be 18.6 newtons. Okay. Right, question 4. Now we have a plate. We've got 3 forces acting on this plate, each in the coordinate direction. One along the x direction, F2, one along the y direction, F3, and one acting down the z direction. So F1, which is 60 newtons, and the coordinates of the plate is in the plane xy plane, and there's 2 points at 2 corners A and B, and we want to calculate the moment of each force along that line AB. So there's a few things to do. We need to note the coordinates of A and B, turn all the vectors, the forces into vectors, get a vector along AB and a unit vector, and do our cross product and dot product calculations. Right. Determine the magnitude of the moment of each of the 3 forces about the axis AB. If it's saying Cartesian vector approach, it's using coordinate vectors, and you do this the calculation in terms of vectors and not geometry. So it's it's trying to get you to not do it in a geometric sense. Okay, what do we need to do? Now let's first of all write down our coordinates so we're clear from the start. 0, 1.5, 0. For A and B is equal to 2.0, 0, 0. We're going to use the line AB, so the vector AB is going to be B minus A, which is equal to 2 minus 1.5, 0. Magnitude of AB is, you know to do this now, plus minus 1.5 squared plus 0 squared comes out to be 2.5. Unit vector along AB is equal to AB, the vector AB over the magnitude AB, which is simple again, 1 over 2.5 times minus 1.5, 0. We can leave it or we can calculate it precisely. I'll write it down for you. So 0.8 minus 0.60. We have F1 is equal to 60 newtons. A vector in that direction, well, we know it in the negative z direction. So F1 vector direction is equal to 0, 0, minus 1. So F1 as a vector is equal to 60 times 0, 0, minus 1, which equals 0, 0, minus 60. Okay. The moment of this vector about AB is what we're being asked. So the moment of F1 is equal to the unit vector along where we want the moment calculated, dotted with the cross product OA crossed with F1. Okay, let's just do that cross product first. So OA cross F1, and we can do it using the determinant notation. So we I, J, K. OA is 1.5 naught. 1.5 naught. Let's clear that. And F1 is if we calculated 0, 0, minus 60. Cross product doing the determinant calculation, we have I 1.5 naught, naught, minus 60 minus, remember there's a minus there, 0, 0, 0, minus 60, clarify that, 0, plus K 0, 1.5 naught, naught. Expand that a bit further, so we have I 1.5 times minus 60 minus naught minus J 0 minus naught plus K 0 minus naught. So the cross product there is going to be minus 90I. We could leave it as that, but I'll just leave it for completeness. 0J plus 0K. Okay. Let's complete the moment calculation. MF1 is the unit AB, and we have that as 0.8 minus 0.6 naught, dotted with minus 90 naught, naught. We do that simple calculation and it comes out to be minus 72 Newton meters. And we can put units on there, Newton meters, because we started with newtons and meters in our coordinates. Okay. Now we could have actually done this calculation as a single determinant calculation. Let me just write how we could have done that. So we could say that MF1 is equal to UAB dot OA cross F1 vector. And we can write that whole vector as this determinant calculation. As UAB is the first line, A minus 0.60, OA is the second one, so the same as the determinant above. 0, 1.5, 0, 0, 0, minus 60. And we do the full determinant calculation, and that would come out to be minus 72 Newton meters. So actually that second calculation turns out to be a little bit easier. It's done, essentially done for you as you do the determinant calculation. Okay. What about the other two forces? So we have F2. We calculate that as the magnitude is equal to 85 times by the vector, which is just 1, 0, 0. So the vector becomes 85, 0, 0. The moment of F2 is equal to the unit vector AB times the point OA crossed with F2. We can do this in the whole determinant calc. So we write the UAB 0.8 minus 0.60, OA 1.50, F 85 0, and it turns out that this is 0 Newton meters. Now, if I was doing this calculation and I got 0, I'd go back and check very carefully, because it's very easy to do a mistake when you're doing your determinant calculations, but 0 is the correct answer. F3, the force vector, well, it's 45 the magnitude times the vector, 0, 1, 0. So a unit vector in the line of it, those are unit vectors. So the actual vector is 0, 45, 0. The moment of F3 is equal to U AB, so it's dotted with OA times F3 as a vector. So we can write that in the determinant form. You see it's only this last line that has changed. If we do that calculation, it turns out to be 0 Newton meters. Probably should write my meters as lowercase here to get it to be correct. Now, why are these new? And this is correct answer. Why are these? 0? Well, they're 0 because they're in the same plane as the line AB. So any vector that is acting in the plane of the line along a point on the line is going to cause 0 moment. So with 0, we can determine that straight away before doing the calculation. It's good to do the calculation to show that. So, question 5 here, the last question. So, this is about vector equations of planes and lines. And essentially we've got 3 points in space, A, B and C. And those define a plane in geometry. We can draw a plane through 3 points in space. We want to, and that triangle is part of that plane, so we want to find the equation of that plane. And then we want to calculate the equation of a line that passes perpendicular to the plane through the centroid of the triangle. So there'll be some point here acting out. I want to find the equation of that line. Okay. So first things to do, ensure you've got the geometry to hand. So we need to just write down the coordinates at the start. So A, 0, 1, 1. B equals 0, 3, 4. C equals 3, 5, 0. Those are our three coordinates. Make sure you agree with those. We want to find two vectors in the plane. So I'll just choose A, B and AC. You could do BC, BA, if you like, whichever. Two vectors in the plane. So B minus A is 0, 2, 3. AC, C minus A, which is 3, 4 minus 1. If we cross product a normal vector is the result of the cross product of two vectors in the plane. Now we have A and B in the plane, and AB and AC in the plane. We'll cross those and we'll get a normal vector. So let's do that. AB crossed with AC. Now we'll do it with the determinant form, IJK, 0, 2, 3, 3, 4 minus 1. I'll expand this for you. And with the minus sign there. Not 2, 3, 4. Expanded now. I 2 times minus 1 minus 3 times 4 minus I not minus 3 times 3 plus K not minus 2 times 3 works out to be minus 14I plus 9J minus 6K. Equation of plane is of the form R dot normal to the plane is equal to A dot N, which is a point in the plane times a vector. So we can do that A dot N. So any point, let's choose point A. Point A was on 1, we could choose any, dotted with a normal, which is minus 14, 9, minus 6. We do that cross product, dot product, and that gives us 3. So the vector equation of the plane is simply R dot N equals 3. We could write in place of N that actual normal vector. So we could write this as R dot minus 14 I plus 9J minus 6K equals 3. We could expand it, but I'll leave it at that for now. So we need to find the line, equation of a line, leaving the centre of the triangle going outwards. So I'm going to move on to a new page here. So centroid of the plane is the mean of each coordinate. So the centroid, I'll call it C for now, is just for x, so it's 0 plus 0 plus 3 over 3, 1 plus 1 plus 1 over 3, and 1 plus 4 plus 0 over 3, which we could write down, and it turns out to be 1, 3, 5 thirds, which equals 1, 3, 1.667, if we like. And it's quite simple to write the equation of a line now, because we have the normal to the plane, which is a vector in the line. So R equals C plus T. T is not a vector. T N is in fact our answer. Well, this is C. N is the normal we've already calculated, so we can actually fill that in with the numbers that we have. 1, 3, 5 thirds plus T, some arbitrary number, minus 14, 9, minus 6. And that's the answer. That's the equation of the line going through the centroid of the triangle and normal to the triangle. Okay, I hope that's been helpful.